Welcome back, dear students. In this lecture, we are going to see the graphical representation or conformation of second order reaction. So, second order reaction can be confirmed by graphical methods. There are different types of graphical methods. So first of all, we'll see the graphical representation method for equal initial concentration. So, for equal initial concentration. Okay, so the formula for rate constant of second order reaction having equal initial concentration can be written as K is equal to 1 upon T x divided by A into A minus X. So this is the formula of second order reaction with equal initial concentration. So what we have to plot on x-axis we have to plot time, and on y-axis we have to plot the x divided by A minus X. Okay, so we have to transform this equation into straight line form, in which this term will be plotted on y-axis and the time will be plotted on x-axis. So we can transform like this: x divided by A minus X, which comes on the y-axis and is equal to A K T. Okay, so this A goes here on the left side and T goes on the left side. Okay, so we have got this. So this is on y-axis is equal to, this is M X. Okay, so here there is no intercept. Okay, simple. Y is equal to mx, it is the equation. So on y-axis we have plotted this x divided by A minus X, and on x-axis we have plotted the t. So if we draw the graph like this, we will get straight line passing through origin, because it is having no intercept. Okay, and what is the value of slope? So m is equal to slope is equal to k into a. Okay, so how can we calculate the value of k? K is equal to the slope divided by a. So this is the formula by using which you can easily calculate the rate constant. So this confirms the reaction is second order reaction. This confirms the reaction is second order. Okay. Then the next is B. For equal initial concentration, another type. For equal initial concentration, the formula is, as we have seen earlier, 1 upon T x divided by A into A minus X. Previously we have plotted x divided by A minus X versus time. Okay, but now we have to plot 1 upon A minus X versus time. So for this we have to transform this equation in some specified form. So therefore we will transform like this: 1 upon T 1 upon A minus X minus 1 upon A. So while discussing the derivation, I also told you to remember this formula.
So here we have to take the t on this side, so it will become k into t is equal to 1 upon A minus X minus 1 upon A. So this minus 1 upon A, it goes on this side, so we'll get 1 upon A minus X is equal to kt minus kt plus 1 upon A. Okay, so on y-axis we will plot 1 upon a minus x, y is equal to mx plus c. So we have transformed this equation into the form of y is equal to mx plus c, where on y-axis we will plot 1 upon a minus x, and on x-axis we will plot time. And if we draw the graph like this, so here 1 upon a minus x, here time. So if you see the form y is equal to mx plus c, so it is having intercept, so we'll get straight line passing through y-axis having intercept. Now here m is equal to k, that is k is equal to slope, and intercept is equal to 1 upon a. So this is 1 upon a, and slope is equal to k. Okay, so this is another graph that is for equal initial concentration. Okay, then we will see that is C for different initial concentration. Okay, so for different initial concentration of reactants, we have the equation like this: k is equal to 2.303 upon T into the bracket a minus b log to the base 10 b into a minus x, a into b minus x, where a is greater than b. Okay, so this is the formula. Now what we have to plot? We have to plot log to the base 10 b into a minus x, a into b minus x on y-axis, and time on x-axis. Okay, so we will transform this equation to get these values. So we will keep the log to the base 10 b into a minus x, a into b on this side, and we will transform all these terms to this side. So what will become? So k into t into a minus b divided by 2.303 is equal to log to the base 10 b into a minus x, a into b minus x. So we'll write t here. So this is y is equal to x, and this is m. So this is the straight line passing through origin. Okay, so if we draw a graph like this, so we'll get straight line passing through origin, and here we plot log to the base 10 b into a minus x, a into b minus x, and here time. Okay, so it is having no intercept, so here intercept is not taken. So slope m, so y-axis on this, x-axis on time, so m is this, slope is this. So slope is equal to k into a minus b divided by 2.303. So if you solve this, you will get k is equal to, you will get this a minus will be, it is multiplied, this becomes denominator, and this denominator becomes numerator. So 2.303 divided by a minus b into slope. Okay, so by using this equation you can easily calculate the rate constant. Okay, so in this way you will get the I hope all of you have understood this. Then the last is D graph D, fourth graph, for different initial concentration of reactants. We have the same formula, K is equal to 2.303 upon T into A minus B log to the base 10, B into A minus X, A into B minus X, where A is greater than B. So this is the formula. Now we have to plot this log to the base 10 A minus X divided by B minus X versus time. That is, on y-axis we have to plot this, and on x-axis we have to plot this. So we'll transform this equation to get this. So first of all we'll rearrange this equation. Okay, so whatever the term here, it will multiply to this K, and this remains as it is. And so we'll write down like this: log to the base 10 B into A minus X divided by A into B minus X is equal to, so K into A minus B divided by 2.303, okay, and T. So this again can be transformed like this: log to the base 10 B upon A plus log to the base 10 A minus X B minus X, okay, is equal to K into A minus B divided by 2.303 time. And this log to the base 10 B upon A, this is plus. So when we'll transfer on this side, our right hand side, it will become negative. And to cancel the negative, that is to get the plus sign, we have to change the numerator and denominator. So A upon B. So final equation will become log to the base 10 A minus X B minus X is equal to K into A minus B 2.303 time plus log to the base 10 A upon B. Means ही टर्म ज्यावेळी इकडे आणली त्यावेळी मायनस होती, ठीक आहे, मायनस लॉग टू द बेस 10 बी अपॉन ए, आणि ज्यावेळी त्याला आपण ज्यावेळी इथं प्लस केलं त्यावेळी काय आलं, लॉग टू द बेस 10 ए अपॉन बी झालं. आता बघा, ऑन वाय ॲक्सिस वी आर गोइंग टू प्लॉट दिस इज इक्वल टू, दिस इज एम, दिस इज एक्स प्लस सी. ओके, so we transformed this equation into y is equal to mx plus c form. आता इथे काय आपण काय केलेलं आहे बघा, now here we plot log a minus x divided by b minus x. Here we plot time and we'll get straight line having intercept on y axis. So this is intercept. So slope here and this is intercept. So slope ची व्हॅल्यू काय आहे बघा, m ची व्हॅल्यू काय आहे इथं, सो m ची व्हॅल्यू काय आहे बघा, m ची व्हॅल्यू ही आहे. सो m is equal to, that is slope is equal to k into a minus b divided by 2.303. so k ची व्हॅल्यू काय आहे बघा, 2.303 into slope divided by a minus b. Okay, so and intercept ची व्हॅल्यू काय आहे मग, intercept is equal to log to the base 10 a upon b. So this is intercept and this is k. Okay, so this confirms the second order reaction. Okay, I hope all of you have understood clearly the graphical representation of second order reaction. Okay, welcome dear students. In this lecture we will see the pseudo-unimolecular reactions. These are the chemical reactions. These are chemical reactions, okay, in which the number of molecules involved is number of molecules involved is more than one, but still the reaction obey the kinetic equation of first order reaction. Okay, so what is the pseudo-unimolecular reaction? It is the chemical reaction in which the number of molecules involved is more than one, म्हणजे याच्यामध्ये एक पेक्षा जास्त मॉलिक्यूल असू शकतो, पण तरीही ही रिएक्शन फर्स्ट ऑर्डर रिएक्शनचा कायनेटिक इक्वेशन ओबे करतं. अशा प्रकारच्या अशा टाईपच्या सगळ्या रिएक्शन्सना आपण काय म्हणणार आहे? pseudo-unimolecular reactions म्हणणार आहे. ओके, so there are two types of pseudo reactions. In one type the solvent will take part, and in other type catalyst will take part. Okay, so these are the two types of pseudo-unimolecular reactions. Okay, so further we will see the examples of unimolecular reactions. So examples, the first example is hydrolysis of methyl acetate in presence of acid. So this is example of pseudo-unimolecular reaction. Okay, so the hydrolysis of methyl acetate in presence of HCl. Here HCl acts as catalyst, and this reaction can be represented like this. So CH3COO CH3, so this is methyl acetate, plus H2O means hydrolysis, the water present in excess amount, okay, and HCl acid acts as catalyst. So it will gives you this CH3COOH acetic acid plus methanol CH3OH. Okay, so this reaction obeys the first order rate equation. Okay, ही जी reaction आहे ही bimolecular आहे. If you see this reaction, it seems to be bimolecular because it contains two molecules, but this reaction obeys the first order kinetic equation, first order kinetic equation. Okay, why this happens? This is due to the fact that the water present in such a large excess that its concentration, the concentration of water remains practically constant throughout the experiment. Okay, so again the acid added does not enter into the product. Okay, so further this acid acts as catalyst, so it does not go into the product of reaction and does not undergo the change in concentration. So the concentration of acid also does not change, and the concentration of water also does not change because it is in excess amount. So the rate depends only on the methyl acetate. म्हणून जरी दोन मॉलिक्यूल असतील तरी ही रिएक्शन ही फर्स्ट ऑर्डर कायनेटिक इक्वेशन ओबे का करते? याचा रिझन आहे water है excess पर मारता है. Okay, so rate of reaction is only depends on the concentration of methyl acetate. So the rate of reaction is given by dx by dt, as we have seen earlier in early lectures. So K, concentration of CH3 CO CH3. So the rate depends on only the concentration of methyl acetate. The reaction can be studied by removing known volume of reaction mixture from the time to time and titrating it with the standard alkali solution. The final reading is taken after 24 hours. Okay, now if the T0 is initial reading, okay, then TT is the reading at any time t, reading at any time t, and T infinity is the final reading. Final reading is taken after 24 hours. Final reading. Okay, so the velocity constant is K is given by K is equal to 2.303 divided by T, that is time, log to the base 10. Here T infinity final reading minus T0 initial reading divided by T infinity minus reading at any time t. So by using the formula you can easily calculate the rate of reaction. The second example is inversion of cane sugar. So the second example of pseudo-unimolecular reaction is inversion of cane sugar. Okay, so inversion, or it is also termed as hydrolysis of sucrose. So cane sugar is known as sucrose. Okay, sucrose is the cane sugar. Okay, so the inversion or hydrolysis of this sucrose in presence of H plus ions, as catalyst can be represented as follows. कैसे represent करना होगा? C12H22 O11. So this is sucrose from cane sugar plus H2O that is hydrolysis in presence of H plus as catalyst. It will give C6H12O6. This is glucose plus C6H12O6. This is fructose. Okay, so the rate of inversion, depends on concentration of sucrose only. Okay, because concentration of water remains constant throughout experiment, and concentration of H plus does not take part in the reaction because it acts as catalyst. Okay, so this change can be studied by measurement with the polarimeter. So this experiment is known as polarimetry because the sucrose rotates the plane of polarized light to the right side and the resulting mixture is lever rotatory. Okay, so if alpha 0 is equal to angle of rotation at the beginning. Okay, and alpha t is the angle of rotation after time t,
alpha infinity is equal to angle of rotation when reaction completed, that is final reading completed. Then the velocity constant k is given by k is equal to 2.303 divided by time log to the base 10 alpha 0 minus alpha infinity divided by alpha t minus alpha infinity. Okay, I hope all of you have understood the types of pseudo-unimolecular reactions.